So I'm not recording any of you guys. I'm just recording me. So, and then I'll put it on YouTube. Does that sound good? The Microsoft Share thing, I don't think really works. And I'm also not going to edit it. It's just going to be all the notes. Did that start lagging when I pressed that button? Because it's recording right now, just me. I'd be really surprised if it did. That'd be really weird. Okay, anyway, so we have three forms of our quadratic functions. This chapter, this unit, we're going to be moving between those forms, so we need to be able to turn like standard form into factored form. That's a goal. The other thing we need to be able to do is turn factored and vertex form into standard form. We're not really going to go from standard form to vertex form, but we're going to move them around. So we need to be able to turn them into other things, because if we have standard form and we want the roots, it's really easy to get the roots from factored form. So let's turn this thing into this thing, and then we can use this to find the roots. There are other ways to find the roots, of course, but that's the easy one. That's a way to do it. There's also the quadratic formula, which we could use to find the roots for this. The other thing that we can do is turn this into standard form. And that's what we're going to do today. So we're going to talk about practice using the area model and distribution to turn this into standard form. Okay? So you didn't need to write any of that down, but you do need to write this down. The name for that, the math language that we use to describe going from factored form to standard form, in general, is called multiplying. You're like, Mr. Martins, duh. We got two parentheses. There's a multiplication symbol between them. Yeah, it's called multiplying. Binomials. So we're going to do multiplication. Like 2 times 3 is 6. Right? We know what multiplying is. This binomials word means 2. Bi means 2. So like bicycle. Bicycle has 2 wheels. Tricycle has 3 wheels. A quadcycle, I don't know what that is. A monocycle, they call that a unicycle. I don't know why they switch prefix types there, but mono meaning 1, uni meaning 1. Okay. So multiplying binomials means 2, bi for 2, and nomials means number. So 2 numbers. Now, if our numbers were just like 3 and 4, and we added those together, we would get 7. So that's just one number still. For 2 numbers, binomial has a variable in it. This is going to look like mx plus b, right? We have an x here, or like 3x minus 4, or x plus 2, right? I can't simplify this any further because we don't know what x is yet. It's a variable. So it could be a lot of different things. And so our binomial is 2 numbers. We have one number here. This is some number we don't know. And then we have a constant. So we're going to multiply these together, 2 of these together. That's what factored form is, right? We got parentheses with a variable and a number on the end. So we're going to use this example. This setup equation is we want to multiply x plus 2 times 2x minus 3. And we're going to turn this into factored form. That's our goal. Turn that into not factored form. Turn that into standard form. Turn that into standard form. Now, there's 2 ways to do this. There's more ways. We're going to go over 2 ways to do this. So we have 2 methods. We're going to start with the more complicated one, the one that I want you to use the most. There are patterns to this multiplication. There are shortcuts, and we'll do a number of examples to talk about those. But this method is why I wanted you to write down A, B, and C when we were doing negative B over 2A. So we're going to use this thing called the area model. I really need new pens, huh? The area model. And the area model uses the area of a square, and it looks a lot like, because it basically is, Punnett Square. And so if you remember back to biology, or if you remember biology, if you're in bio, I don't remember which years those things are taught. When we're talking about genetics and the odds that someone has like brown hair or red hair, like my wife is a redhead, and my child might be a redhead, but it's kind of unlikely because being a redhead is a recessive gene. And so I'm not a redhead. So it's possible that she's a redhead, that Ruth's a redhead, but unlikely, right? Because dominant traits overwrite recessive traits. Even if you have both genes, the dominant one shows up, right? So used a Punnett square to kind of calculate the odds for those things with the capital letters and the lowercase letters. So that's what we're going to do. If we want to multiply some binomial times some other binomial, we would use our square. We're going to use this rectangle. Or the squares are rectangles. So it doesn't matter where the A, B, and C, D go. Well, it matters a little bit. The A, B needs to go together, and the C, D needs to go together. But you could switch which one's on top and which one's on the left. Hopefully this looks familiar. You did this in Algebra 1. I know you did, because I taught it in Algebra 1. Maybe not to you, but so I've kept the setup the same color here. And I'm going to switch colors. And this is called the area model because we're going to find the area of the square. We're going to multiply the sides of each individual square and then add those all together. So just like, here, let's do a numerical example. So if I had this side be 2 and this side be 3, it would total to 6, right? 2 times 3 is 6. But I could also split this up and do 1 and 1 and 1 and 2, right? 1 and 1 add to make 2, and 1 and 2 add to make 3. These are just random numbers I picked. And then we can multiply them, and they should all add up to be 6. If I find the area of these 4 individual squares, this is 1, this is 1, this is 2, and this is 2, I'm multiplying 1 times 2 to get 2, and 1 times 2 to get 2, and then 1 times 1 and 1 times 1. If I add these all up, I get 6, which is the same as just multiplying 2 times 3. So we're going to do that same thing. You don't really need to write this down. I'm just explaining how I'm going to do this thing with some real numbers. So we're going to multiply the sides of each square to find the total area. So A times C is AC. B times C is BC. A times D is AD. B times D is BD, right? These are just variables. And so this is equal to AC plus BC plus AD plus BD. All the pieces added together. Now, when we're finding the area, when we're multiplying the two parentheses, we need to make sure to multiply everything in here by everything over here. It's really common to multiply the first number by the first number and the last number by the last number, and then forget these middle two. Forget those. That's not right. You need all 4 pieces. And it's 4 pieces because it's a 2 by 2. It's like a Lego block, right? So let's go back to our example. Our example was x plus 2 times 2x minus 3, right? And so x is a, 2 is b, c is 2x, and d is negative 3. And if I'm going too fast, please tell me in chat or something. Okay. So we're just going to take the pieces of our multiplication, this stuff in parentheses times this stuff in parentheses, and assign it to the square side. So we can do x here, 2 there, and then 2x and a minus 3. So then we just multiply the sides of the square, like we did here, to get the insides. So x times 2x is 2x squared. X times x is x squared, right? This is not 3x's. We're not adding these two together, we're multiplying them. This is 2 times 2 times x, so that's 4x's. And negative 3x, and then negative 6. So we're multiplying the pieces of the box that meet here. And then we're going to add them all together. So 2x squared plus 4x minus 3x minus 6. And, oh, my picture's in the way, but yeah, so I'm just writing out the contents of the box. We're going to add all these pieces together to get the total area of the box. Now, there's a pattern. For every single one of these, the diagonals usually combine. If I say every and then usually, it's like the qualifier changes the usefulness of the statement. But for our quadratics, if we're doing a binomial times a binomial, they're going to combine every time. Next chapter, we're going to get boxes that are bigger, like a 4x2 or 3x3, and sometimes the diagonals don't combine. But we'll get there when we get there. So these two combine. They're like terms. So the 4x and the negative 3x are going to combine. We need to simplify this statement. 4 minus 3 is 1. So now this is in standard form. A is 2, B is 1, C is negative 6. This method is especially useful when one of the binomials, or both, have an A value or a number in front of the X here, like this, because it just makes it slightly more complicated. Okay, so that's one of our methods. Yes, Brian. Yeah. So next chapter, we're going to do stuff like, let me write it on another piece of paper so that it's not, this is not part of your notes. Next chapter, we're going to do stuff like this. So we have a quadratic that we're multiplying by a binomial. Or we'll do stuff like this, where we have 3 binomials that we're multiplying. And so that'll make our box bigger. But not yet. Not yet. We don't need to worry about that. Right now we're just going to have a box with 4 things in it. But the diagonals usually combine. These two diagonals, not the x squared and the negative 6. Those are not like terms. But these two terms, as long as you set your x's to be on the top and the left, and the constants here, it will look like this. Okay. So our second method, our method 2, is to just distribute. And this method is faster. It's less writing things down because we're going to go straight from this to this line without drawing the box out. Now that can be helpful if we're really comfortable with keeping track of all these numbers. But for some of us, and this isn't an indictment, it's not a bad thing, it just is reality, we're going to forget something here. We're going to get 2x squared, and we're going to get -6, and we're going to forget these 4 and -3x's. And so this method, the distribution method, is going to be less helpful because it will get the answer wrong more often. And I forget things too. Don't get me wrong. This method is super useful because it keeps track of everything. Okay, sometimes this is called FOIL, but I don't like calling it that. So let's use our A, B, and C again. So just 2 numbers added together times 2 other numbers added together. And what we're going to do is we're going to use little arrows to keep track of our distribution. And you've done this before. Like if you're doing, I don't want to cover up the notes, but I just don't want to write on that page. If you're doing 3 times x plus 2, right, we're going to distribute this 3 to both things, and it becomes 3x plus 6. We're basically doing that same thing, except this, instead of a 3 here, we have more stuff to worry about. Okay. So we're just going to draw the arrows or lines, arcs, to keep track of everything being multiplied. So we need to multiply everything in here by everything over here. So this A needs to be multiplied by C and by D. In other words, we can say, okay, well, it's A times C plus D. Okay, and then we need to multiply B times C and B times D. Now I would skip this step. I would skip this step and I would go straight to, well, if it's A times C, that's AC. And if it's A times D, then that's AD. And if it's B times C, that's BC. And if it's B times D, then it's BD. So I'm just using the arcs and the lines to keep track of multiplying everything out. And this should be the same as what we got up there. Okay, so for our problem that we've already done, I'm going to use that same example. It would be x plus 2 times 2x minus 3. I'm running out of room, but it's okay. So we would do the same thing. We're going to draw the arcs. So x times 2x and x times -3, and 2 times 2x and 2 times -3. And so this gives us 2x squared minus 3x plus 4x minus 6. So I'm just using the arcs to do the multiplication in my head. Oh. So x times 2x is 2x squared. X times -3, -3x. 2 times 2x plus 4x. 2 times -3, -6. So we haven't lost anything. We've kept all the information. And this just simplifies to what we had before. Okay. I'm going to give us a minute to ingest. Okay. So I'm going to do one more example. And then we're going to talk about some special cases where there's some special patterns. You don't need to memorize those because you can just use the Xbox method. You can just use the area model, or you can distribute. But if you notice the pattern, it can be helpful over time. Okay. So I need a new piece of paper, but you may not. So can I get in chat? I need 4 numbers. So just 4 different people. Give me an integer and just type it in chat. Cool. I need 2 more. 5x minus 6. 3 cubed is too large. Brian. I could use 0, but it will make the problem trivial. So 2 Ella, and I need 1 more. We'll do plus 5. Cool. All right. So we want to go from factored form. We could find the roots for these, right? They're going to be fractions, but you set this equal to 0 and solve for x. So we want to turn factored form into standard form. We just want to multiply this out. We got some stuff in parentheses. There's multiplication in between these 2 parentheses. We don't write it, it's just assumed. And then we're going to multiply it by this stuff. So the way that we're going to do that is we're going to use the area model. I would not do this problem in my head. You're going to have to write some stuff down. There's too many numbers to keep track of. And even if you've been doing math for a real long time, why make your brain do all that when you have a piece of paper that will keep track of things for you? So, well, let's do the problem. So 5x minus 6, it doesn't matter if we put that here or here. So I'm going to put it on the left. And then 2x plus 5 can go on the top. So this is the length of my rectangle, and this is the width. And we're going to multiply those to find the area inside of here. Okay. So each individual box is going to have a different number in it, and then we'll combine all those numbers at the end. And it shouldn't, yeah, we'll have some simplifying to do, but no canceling. So 2 times 5 gives us 10, and then x times x gives us x squared. For quadratics, you're always going to have an x squared in this box, right? Because it's going to be x times x. And then you're always going to have negative 6 times 5. It doesn't matter what order you fill the boxes in a constant. Now, it's very easy for us, if we're not using the area model, to make the mistake that we're done at this point. If we're not using the area model, we won't see these 2 empty boxes, and we'll be like, all right, I multiplied 5x times 2x, and I multiplied negative 6 times 5, and then you ignore the fact that you got to multiply this 5x times this 5 still. So it's very easy to say this is the answer, even though it is not the answer. So 5x times 5 is 25x. We got to finish the problem, right? And 2x times 6 is negative 12x. And so these two are going to combine. So we get 10x squared plus 25x minus 12x minus 30. And then we're just going to combine these two things. They're like terms. They both have the same variable. So 10x squared plus 13x minus 30. That's in standard form. The homework I assigned is like this. So I signed it yesterday. I know some people complained about the fact that I did that, but sorry. Still due Sunday, so we don't need to stress about it. Now, there are some special cases. Special cases. Whoa, that was weird. Can I have another number that's between 1 and 10? That's an integer number. I need someone to give me a random number. I guess I don't need someone to, but we'll use Evelyn's number 1 here. So 12 is too big. So there's the special case where the values are the same, and then there's the special case where the values are opposite. Actually, I don't want to use 1. We'll use 3. So for example, x minus 3 squared. This is the same as if I wrote x minus 3 times x minus 3. Right? The square just means multiply it by itself. So those are equivalent. Those are equal. So if we do our box method, what I mean by the same is that this negative 3 and this negative 3 are the same thing. Right, so if I do our box method, we get x squared. I'm going to go through this a little quickly. This is not a problem that this kind of problem, I would not use the area model for. I would do this in my head. But the more complicated ones, like the last problem, I would. So negative 3 times negative 3 is a positive 9. We have an x squared. And then we have a negative 3x. We have 2 negative 3x's. And so whenever they're the same, the middle number is going to be twice this number times x, right? Because there's 2 negative 3's, so it's negative 6. And then the last number is going to be this number squared. The negative 3 squared is plus 9. And so if it was 4, if this was minus 4, we'd have plus 16 and minus 8. So there's a pattern here when the numbers are the same. This is double, and this is squared. Now, I don't expect you to memorize that, because you can just use the area model to solve it too. But if you can recognize the pattern for these, it's going to help you the higher up in math you go, because you'll have to do less work. You don't do this, you just recognize the pattern and go straight to the answer. Now, what if they're opposite? What if we have, switch back to blue. X minus 3 times x plus 3. So the numbers are opposite of each other. Well, minus 3, x plus 3, we get x squared. Sorry, I keep forgetting to switch colors. We get x squared. We get negative 9. And then this is minus 3x, and this is plus 3x, and those are going to cancel out. Those are going to cancel out. So then our answer is just x squared minus 9. Still in standard form, it's just b is 0. B is 0. So this special case, where the numbers are opposite of each other, is going to be helpful for factoring. Factoring is where we go from the equation to the multiplication, back to that. Okay? So the same would be true if it was like x minus 4 times x plus 4. You'd get x squared minus 16. because these two numbers are always going to cancel out if they're the same. Okay?